On November 9th, astronomers spotted something in space that should not exist. A set of razor-straight dust and gas jets shot from 3I Atlas, each holding alignment for over 1 million km, untouched by the object's 16-hour spin. According to comet physics, these jets should be bent, blurred, or smeared beyond recognition. But the 12th anomaly of 3 Atlas just rewrote the rules, and behind every impossible detail are consequences that challenge everything we thought we knew about interstellar visitors. So how did the universe slip this through our defenses without anyone noticing it did not add up? The November 9th frame captures 3I Atlas suspended against the black of space, set apart by a striking arrangement of features. A cluster of white lines radiates outward from the central body, some fanning upward, others branching sideways. Each one is razor-straight and broken and sharp-edged even as they extend far beyond the immediate glow of the coma. Toward the lower left, the direction of the sun is indicated, anchoring the geometry of the scene. In that same direction, a broad faint streak points almost directly back toward the sun itself. This is the antitail, where sunlight reflects off dust particles that lie between the object and Earth, creating the illusion of a tail that points sunward instead of away. The antitail stands apart from the other jets, which shoot out in multiple directions and remain perfectly linear for distances exceeding 1 million kilometers. Each of these streaks emerges from the nucleus, an unresolved bright core at the image's center without any sign of curling, spiraling, or blurring. The orientation is clear with the sun positioned off-frame to the bottom left. The antitailor lines nearly along that axis, while the other jets stretch at varying angles, none showing the arcs or twists expected from a spinning object. The field of view spans millions of kilometers. Yet the jets hold their direction with uncanny precision, defying the expectation that such features should fan out or curve as the object rotates. This image is not an artist's concept or a simulation. It is a direct astronomical record captured by a major observatory and processed using standard reduction pipelines. The antitail may be labeled for clarity, but the real focus is the extraordinary geometry of the jets themselves. Their straightness, length, and alignment are not subtle. They dominate the scene and set the stage for the deeper puzzle. How these features can remain so fixed and so crisp on a body that is known to be spinning through space. The frame serves as both map and mystery, inviting a closer look at the physics that should govern what we see and the rules that 3 Atlas seems determined to break. In July and August of 2025, astronomers tracked 3I Atlas with a series of coordinated photometric campaigns. By measuring subtle rhythmic changes in brightness, what is known as a light curve, they calculated the object's spin rate with unusual precision. The result was a rotation period of 16.16 hours. That is about 2/3 the length of an Earth day. For a body several km wide, tumbling through space at interstellar speed, this is considered a moderate to fast spin. Most comets in our solar system rotate in a similar range. But Atlas's period is now a fixed number in the record, not just an estimate. This figure is not an afterthought. It is the backbone for any physical model of how material escapes from the surface. If the nucleus spins once every 16.16 hours, then any feature tied to its surface, like a vent or a jet, should sweep around with it, tracing out a path as the object turns. Over the course of a day, a jet that starts pointed in one direction will end up facing somewhere else. And this motion is expected to leave a clear mark on any stream of gas or dust escaping into space. The photometric campaign that produced the 16.16-hour result drew on data from several major observatories. Each group independently confirmed the periodicity, ruling out spurious signals from background stars or instrumental drift. The light curve's repeating pattern match what would be expected from a rotating, somewhat irregular body reflecting sunlight as it spins. No evidence of rapid spin-up or slowdown was found in the weeks surrounding the anomaly, and the team's confidence in the period is reflected in the published uncertainty, just a few hundredths of an hour. This single number, 16.16 hours, becomes a critical reference point. It sets up a direct test. If the jets we see are tied to the surface and the surface is rotating, the physics of how those jets should look is dictated by this period. Every model, every hypothesis must account for the fact that by mid-2025, 3I Atlas was spinning at this measured rate. The straightness of the jets, their orientation, and their persistence are all measured against this clock. The word typical matters here. At that rate, covering a distance of 1 million kilometers is not a quick journey. The math is straightforward. 1 million km is 1 billion meters. Divide that by 400 meters per second and the answer is 2.5 million seconds. That is just over 29 days. For every particle in those jets, the trip from the surface to the far end of the observed line takes nearly a month. Now consider the nucleus itself, with a measured rotation period of 16.16 hours. The object completes a full spin roughly every 2/3 of an Earth day. Over the course of 29 days, that is about 43 full rotations. Each time the nucleus turns, any surface feature like a vent or fissure swings around by 360, pointing in every direction before returning to its original alignment. If a jet is tied to a fixed spot on the surface, it should trace out an arc in space as the object spins beneath it. The longer the material takes to travel outward, the more pronounced the effect. Think spiral. This is not just theoretical. Laboratory experiments and computer models have confirmed the outcome. Even with perfectly steady outflow, a jet emerging from a rotating body will begin to spiral, forming a corkscrew pattern that widens with distance. The effect is easy to visualize. Imagine holding a garden hose and spinning in place. The water stream forms a sweeping curve, not a straight line. The only way to avoid this is if the jet comes from the rotation pole or if the gas escapes so quickly that it outruns the rotation entirely. Neither scenario matches what is seen in the 3I Atlas images or the measured parameters. The November data show jets that remain straight and unwavering for more than 1 million kilometers despite the nucleus spinning through more than 40 full cycles as dust and gas make the journey. Under standard comet physics, this is impossible. The numbers do not permit it. For the jets to look as they do, the process that forms them must somehow lock their direction in space, resisting the natural smearing that rotation should impose. This is not a subtle discrepancy. It is a direct quantitative break from what every model predicts. The physics demands smearing. The images show none. That is the heart of the problem. A vibe lines up for explanations, each weighed against the evidence. First, could 3I Atlas have slowed its spin so much that its jets never smear? In typical comets, outgassing acts like a thruster, spinning the nucleus up, not down. The July and August light curves show no sudden drop in rotation, and November images reveal no sluggish, barely turning body. The slow rotation scenario lands in the unlikely pile. Next comes the sunlight-triggered jet model. Picture deep valleys or shadowed ice pockets hidden until sunlight hits at just the right angle. Each rotation every 16.16 hours could trigger a gas puff.